So this is the second tutorial looking at gas properties and the relationships amongst those. This tutorial is going to focus on relationships amongst the four states of a gas: pressure, volume, temperature, and the amount. We'll look at it conceptually, graphically, and then we're going to develop an important equation, the ideal gas equation, to finish, and then we'll do practice in class and extend it from there. So let's get right to it. We're going to first talk about the gas law that was discovered first by Robert Boyle way back in the late 18th century. So this is Boyle's law, which relates pressure to volume. So I'm going to show you a simulation of this using the PHET simulator that we looked at in class a little bit. Okay, so we have a gas in a container where we can control various variables. We have volume, which can be changed by this handle. We have a thermometer. We have a pressure gauge, and I have a pump that can let more particles in, or I even have a lid right up here that can take particles out. So I want to look at how pressure changes with volume. So if you go over here, if you look to the top right, we got to make sure we keep other variables constant. So in this case, we want to keep the temperature constant and the amount of particles in there constant by not letting in any more or out. So we're going to take our first situation where I have the handle, this wall right here, as far to the right as possible, and it lines up kind of over the 7 here, and this wall is to the 10. So we can say our volume is proportional to the width, which is roughly 3 units. So if we look at the temperature, 300, our pressure is around 0.8 to 0.9. It fluctuates because of the random motion of the particles. So let's expand this. Okay, let's see if I can do that. And I expand it. I'm going to expand it to roughly to the 4 place. And what do I see about the pressure? Okay, I see that it has gone down. And if I look closely, it's around 0.4 to 0.45. And if I recall, our original pressure was around 0.85 to 0.9. So we can make the rough approximation that it's gone down by a factor of 2, and we've doubled our volume by a factor of 2. And notice that our temperature is still the same. And let me expand it a little more. I'll go all the way to the 1, which would be tripling our original volume. And we see that we're around 0.25 or so. So we're around a third, a little less than a third of our original. So that's a very important conclusion we want to make about this. All right, so back to our note sheet. So according to Boyle's law, pressure is inversely proportional to volume. Okay, so if we were to graph pressure here, volume here, we would get our classic inverse shape, a hyperbola. So we want to understand why is that. From a particle standpoint, why do we have less pressure when we have greater volume? Well, let's think back to the previous tutorial. What does pressure depend on, and where does it come from? It comes from collisions between the molecules in the wall. And so it would make sense that if we want to exert a higher pressure, there's got to be more force. So how do you get more force? Well, the obvious way is the particles are going to go in faster and faster. But if we look at these, so I'm going to change the volume again, slowly-ish, okay, and let the temperature come down. So the temperature rose, if you didn't pay attention, it's coming down. We'll talk about that. If you look closely, the particles aren't moving faster, but what's happening is that they are hitting the walls or colliding with each other more frequently. So it almost gives the illusion that the particles are going faster, but that's not quite it. So what we want to understand about this is, because we kept the temperature constant, that means by definition the average kinetic energy of the particles has not changed, which means they're not going any faster, which means they're not hitting the wall any harder. So we still have to explain why the pressure would go up when the volume goes down, or vice versa. Well, we said just a minute ago, less volume changes the frequency of the collision. So we have a less volume is equivalent to an increased rate of collisions, and the amount of pressure is dependent also on how often the particles hit. And so they're hitting more often, and so we have a greater pressure. And if we expand it, and I'm going to do that one more time because there's something else we want to illustrate with this. Okay, so if I expand this, we can, if you follow any particular particle, you will see it's just not going to hit the wall as often. Okay, so we might ask, how do we keep the temperature constant in this case? Because if you pay close attention, if I contract this again very quickly, the temperature shoots up and then it drops. And if you pay attention right here where the ice is, the ice comes up in the heater part right here, if you didn't see that, I'm going to expand it again. Watch as now the fire comes up, or actually when it, okay, so there's a delay on that. I'm going to bring it back. See the ice coming up. So what's going on is when we compress it with the wall, we're doing work on the particles, and that work goes towards giving the particles energy and raising its temperature. So to keep the temperature constant, you have to let heat flow out of it. That's the point of the ice, to make the surroundings cooler than the inside, and then you can achieve a constant temperature. So if we want the temperature to stay the same more or less the whole time, when you do this compression, changing of volume, you want to do it slowly. If you do it rapidly, then the work done is so quick on it that the particles will gain kinetic energy very quickly rather than really slowly, and not be able to achieve equilibrium with the surroundings. Okay, so generally when we do Boyle's law, your compression or expansion is going to be slowly done. All right, so there's Boyle's law. Next one is called, well, actually, let's investigate first, and then we will do the other ones, just talk about them. So next one we want to look at is pressure and temperature. So let's see how those are determined using this system. So in this case, we're going to click over here, and we're going to keep our volume constant. Okay, so let me see if I can get out of Smart Notebook here. All right, so we're going to lock this so we can't move it. So we have a pressure. It's at around 0.3 atmospheres, and we're going to increase the temperature. And we can increase temperature with this control right there. It's pretty straightforward, and so you can make a silent hypothetical hypothesis about what's going to happen. It shouldn't be a big surprise. So as I add heat to it, so we see our temperature rising, and we're up to 600, 700, 800. Okay, so I've essentially almost tripled our, let me see if I can get up to 900. Oops, I went past a little bit. Let me come down with the ice. All right, so I guess that's around 900. And if you look at our pressure, it originally was around let me get up to, let's go up to 1200 if I can. All right, so 1200, and we're at 1.3. So we've essentially quadrupled our temperature, and we have very nearly quadrupled the pressure from before. Okay, so let's bring it back down just to verify. So we're around 1.3 atmospheres. And if I remove heat, we see that the pressure drops. And if I come down to around 300, all right, we're at about 0.3 something. So 4 times that would be 1.2. And we can see a fairly simple relationship there. So to summarize, we have pressure is proportional to temperature. Okay, and this is called the Gay-Lussac law, named after a Frenchman. All right, and so why does this happen? Why does an increase in temperature give us greater pressure? I think this is of the three the easiest to understand from a microscopic standpoint. We know that a greater temperature, because of the heat impact, gives us a greater impact speed. Why does it give us greater impact speed? Because greater temperature goes to a greater average kinetic energy. It must, by the law of conservation of energy. So if all the particles on average have a greater kinetic energy, they're going faster, they're going to hit the walls with more impact and impart a greater force. Less obvious, but just as important, is because they're moving faster, they're going to hit at a greater rate, just like we saw earlier with a smaller volume. So you have a double contribution from that. All right, how about mass? What if we increase the mass? That's easy to check on here, so why don't we do that? So we got a pressure right now of 0.32. We've got a steady volume. So I'm going to pump in more particles. Let's see if that matters. All right, it seems that our pressure has gone up a decent amount. We'll add in even more. Our temperature is holding. There's no reason why it should go up. We're not doing work on the particles within the box. Yep, and if we keep adding and we keep adding, our pressure goes up and up and up. And if we remove our lid, whoops, and we let the particles escape, and now we see our pressure dropping. And we also see, if you're looking carefully at our temperature is dropping as well. That's a little less obvious why that's happening, okay? So I'm not going to address that right now, but we can certainly talk about mass. All right, so mass is simple enough. More particles simply means more collisions. If you have more collisions, you have more pressure. So if we do pressure versus mass, it's pretty straightforward. All right, the last law we want to address here is something you may have remembered from chemistry, is Charles's law. Okay, I'm not sure where the apostrophe goes. And that looks at the relationship between volume and temperature. So with the simulation, it doesn't work as well, so I'm just going to give you the law and the graphical, and then we'll just put it all together, right? So volume turns out is directly proportional to temperature. So if you double the temperature and you leave pressure constant, that's really, really important, you're going to get twice the volume. That's something I can show you in class with the heat engine. So if we do volume as a function of temperature, we get something like that. All right. So if you take a balloon that's allowed to expand and you put it in a warm environment, it will get bigger and bigger with the temperature. But the pressure does not change. Okay. So how does this work? This is a little bit more abstract conceptually. So if the pressures remain constant, we'd expect a greater impact speed because of the greater temperature. So that we would think will make the pressure go up. But we can offset that impact speed effect by lowering the frequency of collisions by having them hit less frequently. How do you do that? We have a greater volume. In other words, if we have a greater volume, they're not going to hit as often, but they're going to hit harder, so the net result is a constant pressure. So long story short, if you increase temperature, you have to increase volume to keep pressure the same. Okay, so you think about that. Make sure you understand that logic, because you want to be able to describe that in the test or quiz. All right, so let's put it all together. We have 4 different relationships there, and so if we want to look at all the effects of that based on pressure, we saw that 3 things affect pressure: volume, temperature, mass. And so if we look at the graphs from above, we see that pressure was directly proportional to temperature, it was proportional to mass, and it was inversely proportional to volume. Okay, so that's one way of looking at it. I can bring the V over to the other side, and I can say PV is proportional to MT. I'm just going to switch those around. And sure enough, I see Charles's law here. Volume and temperature are proportional. Here is Gay-Lussac law there. And then the P and the V being on the same side is Boyle's law. And then there's the mass law. All right. So what we're basically saying is, if I bring everything to one side now, okay, what I can say is the pressure of a gas times the volume of gas divided by the mass of a gas divided by the temperature gap is equal to a constant for all gases. Okay, or put another way, for a given gas at its state, if I have a certain initial pressure state and a volume state and a temperature state, it's got to equal the P2 V2 over T2 at any other conditions. So if I have a balloon under a certain pressure, a certain volume, and a certain temperature, and I change one of those parameters, let's say I double the temperature, then something has to change about the pressure or the volume to keep that ratio constant. So we will develop problems, those proportionality problems later on, because they're very, very useful. So this implies an equation. Okay, so I'm going to jump right to it, in that we can say PV. So in the form that I had right here, which I've crossed out, the only reason it's not an equal sign is because I'm missing a proportionality constant. So that proportionality constant is called the gas constant. So the equation is called PV equals nRT, where R is the gas constant and N is the number of moles. It turns out that if you don't express the quantity in terms of moles, then R will take on different values for different gases. When you have the quantity expressed in moles and R is the same value, it is 8.31, something you may remember from chemistry, joules per mole per Kelvin. Okay, so when you get back from class, or when we come to class, we will do a quick little example of how many moles approximate this room. In fact, I'd actually like to do that tonight. All right, approximate how many moles are in this room given what the standard pressure is, standard temperature, and estimate the volume using the dimensions of the room. Make sure your temperature is in Kelvin, though, and your pressure is in pascals. Okay?